Well, now let's look at this interstellar. As the conceptual model, Stella call it map. In this map, you remember we have 3 categories of human populations. The uninfected one, the infected one we call the hosts, and the one impossible to be infected, we call it immune. And then we look at the 3 equations. The first one we think about this, the human host death, and it's a simple population model. You just multiply the human hosts population times the malaria-induced death rate. The second equation here, a part of the human host recovered and become immune. And then, in that case, we also only need to multiply the immunity rate to the human host population. That's the trivial equations. The most important equation is the third one, and we refined to the fourth one. How the spread disease, how the disease spread, all come from this loop and this loop. So for the human host, a part of them recovered but become susceptible to the malaria again, and then come to this way. A part of the host immune, a part of the host become dead. So there's a 3 way out for the human hosts. The positive way, they come back, become the uninfected human again, and that's the easy calculation. It equals the human host times the recovery rate, just like our SARS model. The negative side, that's the most important connection, how the malaria spread, the uninfected human become infected as a host. And that have 3 components here. That change rate, the derivative, equal the host number, equal the susceptible population number times the probability bitten by the mosquitoes times the probability this particular mosquito is a vector. So these 2 probability add the population to make this disease spread. So if you try, so Bill Gates spent like hundreds of millions of dollars, what he's trying to do? He tried to do this to reduce it. He cannot wipe out all the mosquitoes, but you can change the hygienic condition and also to protect human beings from mosquito bites. So understand in the conceptual level, and here are the key work for the human being to do. Of course, you can try to treat those hosts in here too, to help them to go to immune instead of die, but that's secondary. The primary policy should be change this to probability. Now let's go to the next submodel, the mosquito models. And the assumption of the mosquito is this. We don't count the number of dead insects. There are too many. We can, but it's not much relevant. But we will count the other assumption. The infected mosquito immediately become a host that can infect the human. That's the first assumption. If a human being is bitten by a vector, it becomes a host immediately. So that's 100%, unless it's immune. There's two categories of mosquitoes. We talked that, the uninfected and the infected, the vector. So for new mosquito, when it's born, it's uninfected, and a part of it die. But the mosquito is so small, in our model, we're going to use the simple Malthusian model. Then there's no limit, no carrying capacity, and means the mosquito have abundant food. That's our blood. Okay, now for the mosquito model, pretty much we just think about the birth and death of the two groups of mosquitoes. That one is just common sense. The total mosquito equals the infected added the uninfected, the vector. Number 6 is about the birth rate of these uninfected mosquitoes equals its own population, no, the total mosquito population times the birth rate. And so it's the death rate. The uninfected mosquito death rate equals mosquito death rate multiply the uninfected mosquitoes. And the infected mosquito, the vector death rate follow the same rule. That's just the population model. Then you have a 2 birth model, 2 death model. Now, let's focus the core, the most important part is the vector change rate. So what we concern, either kill the mosquitoes, but the most important is kill the vectors or wipe out the vectors. So first, we make an assumption. The rate of change of the uninfected mosquito to vector is always proportional to the uninfected mosquitoes. And that's again like the population model. It's just equal another Kp. The P is the uninfected mosquito. So again, it's a proportional model. And the two facts affect the rate of change from infected to vector, from uninfected actually to vector. So again, how the mosquito become a vector? The mosquito has to bite a human host. So the first, we look at the probability of the mosquito bite a human. So how much probability this mosquito could bite a human. And second, that a human has to be a host of the disease, malaria. So mosquito bite a human does not necessarily make the mosquito as a vector. You have to bite a host. So that's very similar to the human infected rate. So in this case, the change rate of the uninfected to infected, that's the core of our model, really has this relationship. The derivative, the change rate of the vector formation means the birth of the vectors equal the probability to bite a human, and also the human is a host. Again, that's the product. And then multiply the total population of the uninfected mosquitoes. I hope this makes sense to you. So pretty simple. We apply the population model again and again.